Today's lecture is going to be about, we'll continue the graph algorithms.
I'm sorry, that might be 1 second, please. So, okay, start over. So, hello everybody. Um, Today's lecture 12 is going to be about the graphs. So we're gonna continue. We're now gonna study concrete algorithms. On the previous lecture, we started graph representation. So we know how to store the graph. There are two ways, basically two ways. Um, we studied two ways, adjacency list and adjacency matrix. In most of the cases today, we will use adjacency lists, okay? So we're not going to use adjacency matrix today. So today's question, uh, we're going to understand how to traverse the graph. So this is the first thing you need to do is as soon as you get the graph, you need to know how to traverse it. It means walk on it, how to walk on the graph. So that two things can be done with either DFS or BFS. So DFS stands for depth first search and BFS stands for breadth first search. Okay. So we'll see what's the BFS and DFS is. So before we start, let me just show you a little explanation, like visually. So the simple example of DFS algorithm is the following. So let assume that I opened the Wikipedia and I wanted to study this chapter, okay, this article. And so what can I do? I can have two strategies. The first one is the depth first search. What does it mean? It means that okay, I see okay, so I see what's the algorithm or its properties and so on. Maybe I can study this history. So whenever I read it, whenever I see the definition that is not concrete to me or that I don't understand, that I haven't ever visited, so I open it and start to search for it again. So I watch this definition. Okay. There's a new unknown word for me. I visit it again. Oh, sorry. I visit it again, and so on and so on. Okay. As soon as I finished with the vertex, so this is my vertex. So the page is the vertex. As soon as I understood the entire vertex. So there is no H outcoming. So it means that I understand here everything well. I finish that vertex and come back. Then I go further, read it, and okay, I see yet a new word. I visit it, I see it. Let's assume that I've already processed it. So I come back. Then I finished with that page. I come back and I continue. Okay, I read it, and so on. So I see new word. I open it. I open it. Um, I open it. I open it, I open it. So this could go um, forever, but I mean, there's a finite number of vertices in our graph, right? So if our vertices are pages, so even in Wikipedia, there is a finite number of vertices. At some point, I will reach the vertex from which there's no transition to unvisited vertex. So if I would see a visited vertex, for example, I've been at that vertex called determinированность, and if I will see that vertex here, then I won't go there. Okay, that's the idea. So that's the DFS algorithm. So this is the recursive algorithm, and goes as follows. So it works as follows. This is a simple code of DFS algorithm. So what I'm doing here, I having a I have an array of um, I have an array of integers or maybe booleans um, of length n of number of vertices, which called was, which will indicate if I visited the vertex or not. So I assume that my vertices are numbered from 1 to n, and so I read the graph already. So the code goes as follows. So we run DFS from single vertex. Okay, we run DFS from single vertex. And we set that vertex to true. So we set that vertex, we say it is visited now. And then we go over the edges, over the neighbors of that vertex. Okay, if VU is an edge, so it means that U is a neighbor of V. Uh, and if it's not visited neighbor, I go to it. I run DFS from that vertex. That's it. So that's the entire transition. That recursive function will do traverse of the graph in concrete way. So let us see on an example how it works. Okay, so let us say I start from the vertex 1. So example, I do DFS 1 here. Okay, I start for the vertex 1. So let me mark in this the vertices in a special way. 1 second. We'll roll this back. So DFS1 would go as follows. So DFS1 would go as follows. So I initially mark this vertex as visited. So I'm gonna mark the vertex in with the I'm gonna draw the vertex with the blue. Fill not fill but yeah, color the vertex with the blue color. Paint the vertex with the blue color, meaning that it is visited. Okay. Um, okay. I start from vertex 1 and I put it in the recursion stack. So we have a recursion stack active. So so yeah, from recursion lectures, you might have known that beneath the recursion there is a stack. So I'm gonna display that stack to you. So stack is the um, so the recursion stack is simply a ordered sequence of active recursion like active runs of functions. Okay, so I start the vertex 1, and depending on the edge list, so edge list can be given to me as 5 4 6, or like adjacency list of vertex 1 can be given to me as 5 4 6, or can be given to me as 6 4 5. Doesn't matter. I mean, depending on that or the order the edges are listed, the DFS can change. So it's not always give the same traversal. It can give different traversals. For example, let us say that 5 is the first in the adjacency list of 1. So there's an adjacency list of 1, g of 1, we denote it, is look like, let's say 5, 4, 6. Okay, I go from 1 to 5. I color 5. Now I'm at 5. I go to 7. So I should put here 5. Okay, without commas. Let us say without commas 5. Then I put 7. At 5 I can see 1, it is visited, so I go to 7 only. At 7 I have two neighbors, 5 and 8. Okay, I let us say the list is 5 8, so I check 5, it is visited already, so I don't go there. I go to 8. I run from 8. Now let's say I run to 4, and from 4 I can see that there's no edge, right? I mean there is edge. There is h for 8 and there is h for 1, right? But both of these vertices are visited. So this is the first vertex. So I process this edge, I process this edge. So this is the first vertex that will not do anything. So this is the first vertex um, that uh, do not run any other vertices. So I'm and that first vertex that finished the run. So this I mark it with the filled blue color. So it means that this vertex over. So this vertex already run this DFS and the DFS is over. So I come back to 8 then. So I remove 4. I come back to 8. Then from 8 there is one more edge. I go 6. 6. And from 6 I see there's no 8 1 is already visited, so I don't go there. And um, 8 is already visited. I don't go there either. So I finish vertex 6. Vertex 6 is finished. I put it out of the stack, of the recursion stack. And from vertex 8, 8 is over, 7 is over, 5 is over, 1 is over. So we'll see that this is over, this is over, this is over, this is over. So I visited each vertex only once. I ran DFS from each vertex only once. And I traversed all the vertices in this part of the graph, but there is also this part of the graph. So as we can see, those vertices would never be touched. So this is called, from the discrete course math, you might know that this is called connected component. We will talk about it a bit later. But as for this, like for now uh, we will not touch that. So for now what we done, we visited like some part of the graph. We actually visited only those vertices that are reachable from vertex 1. So that way DFS works. So in order to visit these vertices as well, we need to run DFS from some of these vertices. Okay. So here recursion stack is like just an abstract notion. So we don't actually have this stack somewhere stored, right? So this is already inside of C++. So C++ already keeps that stack for the recursion. So you don't need to worry about it. But uh, you may be aware of it. Okay, so actual DFS, let us draw from top to bottom view of the DFS. So we started from vertex 1, we went to vertex, we went to vertex 5, went to vertex 7, went to vertex 8, and from vertex 8 we went to vertex 4 and vertex 6. Okay, so there are blue edges and there is a, so I draw this, but actually we may leave it without color. Um, So this edge and this edge was never used. So we didn't actually traverse with these edges. We didn't actually use them in DFS. So let us draw them here. So this one would look like this. This one would look like this, right? Yeah. So the blue tree is called blue tree. So DFS produces a tree, DFS tree, which is called DFS tree or DFS traversal tree. Let's just say traversal tree. And um, so the DFS traversal tree is a tree that formed with the edges that were used in transitions within DFS. The edges that are in use are called back edges. Yeah. So that's it. So let us count the asymptotics of the DFS. Um, so note that each vertex that is processed, um, each vertex is processed at most one time. So we visited each vertex exactly one time. I mean, at most one time, one or zero, right? Because there are vertices that are not touched. So that is big O of n. So we have n vertices, that is big O of n, and each edge is processed at most twice. So from each endpoint, this vertex, this edge, and this edge were looked up, or for example, h48 were looked up twice from the vertex 8, from the vertex 8 and from the vertex 4. So this edge were looked up twice. That means that it is 2m number of operations. So in total, we would have big O of n plus m operations. So that's the asymptotics of the DFS. Nothing hard, nothing problematic here. Okay. 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 Let us then proceed to problems that DFS can solve. So we'll proceed to the problems that DFS can solve. So as I already mentioned before, um, there is a bunch of problems on connectivity of the graph, of an undirected graph, that DFS can solve. For example, so let us briefly um, remind, remember what is connected graph. So graph is connected if there is a path between any two vertices of that graph. So path means like, mm, path is just a sequence of edges in vertices, or sequence of vertices that is connected by an edge. So this is the path. So this is the path, or maybe I directed version, doesn't matter. I mean, this is trivial. Okay, and so graph can be connected or disconnected. If it's disconnected, it can contain connected components, as for example in this graph. For example, this graph has two connected components. Okay, so this graph, this connected component. Oh, sorry. This connected component and this connected component. So this graph is disconnected and it has two connected components. And the problem is, for example, to find these two connected components, to like list grouped vertices so that each of the group represents the vertices of connected components. So here's the problem. So given the graph, determine if it's connected, yes, just yes or no, and if it's or another formulation of that problem is find the connected components, just like straightforwardly find these connected components, like list them, as I told you before. So what we can do, we can run DFS from any vertex V, then all visited vertex form connected component of V. So we run DFS from vertex V, some random vertex, and then what we will see that uh, all the vertices that would be visited within that DFS are forming connected component of V naturally, right? So each vertex we can visit, each we can reach from vertex V. That means that this vertex is in the connected component of vertex V, right? So we have undirected graph here. Um, so the code-wise that will look like, so we have a vector, we will have the vector of components, so vector of vectors, integer vectors called comps. So it's just like a two-dimensional array, but vector of vectors. And for each, so we run over all the vertices from 1 to n, and if vertex v was not visited, so that means that we found a new connected component, because because the fs run from that vertex will visit all the components, all the vertices of that component. So we create the vector component comp, which would be a storage for the vertices of that component. Components or components, I would say. Components. Okay, so DFS, so we pass this vector to the DFS with ampersand, so that that will be changeable within the DFS, and we will pass these vertices uh, to this to this vector. So we just add in the beginning of the DFS or at the end, doesn't matter really in this case. So we add here, for example, between DFS definition and was v equals 1, we add component pushback v. That's it. So we're gonna just remember what we visited and store it into the some vector, and then at the end we will put that what we gathered into the vector of vectors. Okay, and at the end we just output the components. That's it. This is very simple algorithm. So another useful thing we can do is to find the cycle in directed graph now. So before this was undirected graph. First problem was for undirected graph. The second one is for directed graph. So what we can do, we can um, so given a directed graph, so the problem is given directed graph, you need to print the cycle or print -1. So the cycle is the path that starts and ends in the same vertex. Uh, yeah, that's it. So simple path that do not use any vertex or edge twice. So this is the example of the cycle. So you just need to find the cycle. So what we can do, so you can pause the video and try to think of how to solve that problem. I will not spoil it for you now. And so now we're gonna dive into the solution. So the solution is the simple actually. We divide three vertices into three types. Oh, sorry, you divide all vertices into three types, as I actually showed you before. So once So on the picture, I showed you that there are three vertices: the vertex that is not visited, the vertex that is visited but DFS has not been over, and the vertex that is visited and DFS has been over, right? Um, okay, so I showed you that before, but actually in the DFS code we did not distinguish such vertices, right? In the code. So now we want to do that. We want to do the distinction. We want to differentiate these vertices. So vertex within like uh, empty black vertex, it means that it's not visited. Empty blue vertex, it means that it's visited, and but DFS has not been finished yet. And blue filled means that it is visited and DFS is finished. So if there is a cycle in the graph, so it means that we will face the situation like follows. So for example, let us assume we started from that vertex. So let's look closely at this picture. So for example, let us assume that we started from that vertex. So we went here, we visited everything here, nothing found. We went here, visited everything here, nothing found. We go, 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 go. So maybe we would have some branches here as well. So like here, maybe, not necessarily, no. Um, and at some point we will face situation like this. So this is the active. So um, where it is, yeah, this here is this. So this is that is the active. So that is that this branch is vertices that has active DFS state. It means like their DFS is not over yet. So we run DFS at some point. We run DFS from each of these vertices in that order, and their DFS has not been over yet. So that means that at some point we'll face what that vertex such that there is an edge like this to the active vertex, to the vertex that has its DFS not over yet. Okay, uh, this is true. We always face that vertex because, for example, there is a cycle in the graph, some cycle. So let us imagine we have a cycle here, and we run DFS in this graph, and at some point we will reach some vertex of that graph or of that cycle, right? At some point we will reach that vertex, and whenever we reach that, we either go this or that direction. This direction, for example, we will go, 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 and at this vertex, we will face that situation. This DFS will be open, and we will go to that vertex. As since it is a cycle, there's that edge, and that edge would be actually a this edge, this uh, bold blue edge. So this edge is this edge. Okay. So if there's a cycle, we'll face that situation, and um, we then can catch this moment whenever that happens, because this is exactly the case when this is exactly the case when um, uh, we we trying to go to the oh, sorry, this is not DFS. This is exactly the case when we try to go to the vertex U, but but this vertex already visited. Okay, but here we actually don't differentiate if it's uh, if it's if it's finished its DFS or not. We just don't care. We only watch. We only want want to know if it's not visited yet here in this implementation. But what we can do, we can color those vertices in three colors. So 0 is visited. So was of v equals 1 equals 0, it is means that it is not visited. equals 1 means that it is visited, but DFS has not been finished, and equals 2 means this. DFS has been finished. Okay? So we can track this moment. If there is an edge to the visited vertex that is of this state, then it means that we found a cycle, and we can retrieve that cycle from the from this sequence, from the stack. Okay, so we can actually one way of doing that is to actually store the stack during the DFS. So at when we enter DFS, we push the vertex into the stack, and when we leave the DFS, we pop this vertex out of the stack. We can actually store a concrete stack, and whenever we hit that vertex, we then just need to roll back to this vertex, and that way we obtain this cycle, right? That's it. Um, that's it for the DFS. I will leave this implementation um, of this problem to you for an exercise, and let us go and try to implement this first problem. So so obtain connected components on the vertex. Okay, so let us try to do that. Okay, so what we do, we read the graph. First, we read the graph. So we will have vector. We will have adjacency lists. This is all we need for the graph. And maybe we have this number of vertices, number of edges. So we read number of vertices, number of edges. So let us do like this. You can do not scanf but seen. I prefer to seen. I prefer to scanf. We iterate over the edges. This is usually how the graph is given via the list of edges. A, B, G of A dot pushback B, G of B pushback A. So this means that uh, there is an edge, undirected edge from A to B, So I push B to A and A to B. So what is required actually? And then in order to obtain connected components of the graph, what I want to do is, I'm sorry, what I want to do is run DFS. Let's say v equals 1, v less than equal n, and if it was if it wasn't if I wasn't there yet, so it means that new connected component found. So I actually can do like this. I can create the comp dfs v comp and comps dot pushback comp. Well, I can actually output this straightforwardly here. So let us actually do this. I'm sorry. Maybe I can print it. Oh, no. I should output first the number. So usually they require you to first output the number of connected components and then description of connected components. So I create here a vector of vectors. So I should put like this, comps. Um, now I print the number of connected components. Let's say number of connected components. Now I iterate over the number of connected components. Oh, sorry, this is This must be a size. Um, oh, I don't have. Actually, I should add it here. You can add this define here if you want. This is much more convenient and short. Comps, CZ of comps, and then j equals CZ of comps I, j plus plus, out, or maybe print. I should print here the size first. Print comp number I of size this number, and then I print it. I says CZ size of comps I, comps ij, and end line. ADS week ADS dot din week, oh okay, week 12. What it says? Oh, it says there's no. Okay, that's true. And DFS. So I add ampersand here, which is very important because otherwise it won't work. Or you can create this in the global scope. So that's also an option. DFS was not declared in the scope. 34. But don't you like Mr. C++? Maybe the comma is here. Yes. So I run DFS. So what I do in DFS, I put this, I mark it as visited. I add this to the vector. I add this vertex to the vector, and then I iterate over the edges of the vertex v. So the other endpoints. The u is going to be the other endpoint of an edge outgoing from v. And if it wasn't visited, then I should just go to that vertex u. Maybe I don't need that. I don't need that either. That's it. Yeah, I forgot to pass comp. That's it. So I need now a graph. Let us a in. Let us actually take this graph for an example. What I have here. I have 9 vertices and how many is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 edges. What are the edges? 1, 5, 1, 4, 1, 6, 2, 3, 2, 9, 3, 9, 4, 1, 4, 8, 5, 7, 6, 8, 7, 8. That's it, 10 edges. I pass the input file. This way I can pass the input file. And that's correct answer. Number of connected components is 2. This 3 vertices is the second one. This vertex is the first one. 157 157846. That's correct. And that's actually the order in which we enter them. 157846. 1578 and then 6. This is actually exactly the same DFS3 were involved here. Okay, that's the implementation of DFS. Let us go further. Next problem we're gonna talk about is So the next algorithm we're gonna talk about is BFS. So BFS is the breadth first search. So in picture, coming back to the example with the, um, 1 second, please. Coming back to the example with Wikipedia. So let us say Wikipedia algorithm. So uh, we're staying at the algorithm vertex called algorithm, and then I read that vertex. So one way I can do that, no, other way we can do that, apart from DFS, I explained you before. Another strategy would be actually to read the entire page. I read the entire page, and then after I read it, I then look at the first non-visited vertex. So for example, I read entire page, and then I see what I don't understand. What I don't understand. For example, infinite loops I don't understand, and Euclidean algorithm I don't understand, and so on. So I first visit all my neighbors like simultaneously. Those are the candidates. I read the page, and then I see the candidates for the next visit. Okay. So I wrote down those candidates. So for example, infinite looks, Euclidean, and enumerate infinite set. Okay. So these three things I don't understand. And then I see, and then I go to the first one. Okay, infinite loops. Okay, I read that page as well, and then I see, okay, pseudocode. I don't understand what pseudocode, but I add it at the end of the list of what I need to read. Okay, because those guys I opened first, I add them. I read them before the pseudocode, for example, before this page. So I open in that way I opened like several pages. So okay, I ended with the finite loop. So I ended with the algorithm, I ended with the infinite loop page. So I go to the Euclidean algorithm. Then here, okay, I read it. Um, so is there algorithm? Oh, so yeah, there is a link algorithm, but it is already visited, so I don't open it. Okay, there is a fraction. I add it at the end of my queue. So I have a queue of things I need to read. So I add it at the end of that queue, and so on. So I open Bizu identity, then I close. Okay, I've done with the fleet algorithm. I go to the computably enumeratable things and so on. And that way I traverse all the Wikipedia page, Wikipedia website. Okay, assuming that this is connected, of course. And I mean, even not connected, strongly connected because it's directed graph. Okay, so that's the idea of the algorithm. So initially, for example, we start in picture, we start from that vertex. So this was our first page. Then we add my neighbors to the queue. Okay, I added these guys to the queue. Um, then I pick up the first one I added. I add then at the end of the queue I add these guys and finish with that. Finish with that. Then I picked up the next one. I add all the neighbors that are not visited yet, so I don't add anything here. And then I add this guy, and then the next one would be this guy, and so on. So we're gonna use, so BFS algorithm is a algorithm that finds the shortest path length DV. So this is gonna be stored in the array DV. It finds shortest path length from start vertex to any other vertex. Okay, so this is the way we can traverse the graph, and I like on the way we can calculate the number, the shortest path from starting vertex to any other vertex. By shortest path means the path with minimum number of edges to that vertex. Okay. So let us consider. So in order to implement that algorithm, we'll use a queue, as I already explained you. And so you have a queue, and we have array dv. dv is the value of the shortest path. So initially we'll set 0 at the starting vertex. So let us say that our starting vertex is 1. And in other vertices, we'll put minus, like infinity, plus infinity. Putting plus infinity in code means that you just put very large number that will not appear in the calculations, like but that is larger than any number that could appear in your calculations. Okay, we start from the vertex 1, we put that into the queue initially, and then we pick up the first item from the queue, we delete it, and then we add all the neighbors that are not visited yet. So what are all the neighbors? Is this guy with 4 or 3, and this guy 3. Okay, and when I add them first time, so I add them only once in the algorithm, and when I add them, I update its dv value. um, I put here 1 and 1. So this value is defined to be the value dv d value of vertex 1 d1 plus 1 plus 1h. Okay, so okay, we have now. So I finish with vertex 1. I take the vertex 2, remove that from the queue, and try to update the and try to go to all my neighbors. So I can go to 3, but 3 is already visited. So the way I check it is actually I can either check if it's equal to infinity or not, or I can check if my transition, so d2 plus 1, is less than 3, is less than d3, is less than d3. So d3 is equals 1, d2 plus 1 is equals 2, so d3 is better actually. So like the value that we got there is smaller than the one that 2 proposes to vertex 2 proposes to vertex 3, so then we will not go to vertex 3. And actually I'll spoil it to you, it will never happen. If we once visited the vertex, we'll never uh, visit it again. I mean, nothing would be better than the first value that we put there. That is the claim. So okay, we continue. We cannot do that for vertex 3, but we can for vertex 6 because it's infinity there, uh, and to vertex 7, and to vertex 4. So we add all these guys into the queue in some order, doesn't matter which one. Okay, for example, 4, 7, 6. Okay, then I finished with 2, I go to 3. From vertex 3, I cannot visit anything. So this 5, there is an h5 3, it goes in one direction. So I cannot go to vertex 5, I cannot go to vertex 1, I cannot go to vertex 2, and I can go to vertex 6, but it's already visited. So I'm done with 3. I go to vertex 4. From vertex 4, I can visit 1 and 8. 1 is already visited, so I put 8. Oh, I'm sorry, I forgot to update the actual information. Sorry, so what I am up to? Ah, okay, okay. So at vertex 2, whenever I was at vertex 2, I must have been updated these information. Whenever I add to the queue, it means that their information is already uh, actual. So it means like to vertex 4, it is 2, it is 2, it is 2. Yeah, I forgot that step. So now we pick up the next one, that would be vertex 3. For vertex 3, okay, we already got that nothing happens. And from vertex 4, I pick up vertex 4 from the queue, I remove it. I'm trying to update the neighbors, and only 8 I can update. So I update its value here. I put 3 here. Okay, and I now put vertex 7. Take out the vertex 7. Uh, I forgot to add 8 here. Yeah, 8 I added. So I pick up the next one. It's vertex 7. Vertex 7 has access to the vertex 9 only among unvisited. And yeah, actually, only outgoing edge is to 9. So we put 4, distance 4 at the vertex 9 and set it to be visited. Add this to the queue. Um, So the way I assigned why 4, if you wonder why it is 4 there, um, I'm answering you that, oh, I'm sorry, because it is not 4, it is 3 actually, because the value of the vertex 7, so the shortest path to vertex 7 is of length 2, and we add this edge, So that would be 3 actually. It is 3, so we add this to the queue, and we've done with vertex 7. We now go to the vertex 6. Vertex 6 is here. We try to update to 7, nothing happens, right? Because 6 has value 2, 2 plus 1, 3, 3 is larger than 2. Nothing happens. Okay, vertex 8, um, again, nothing happens. Vertex 8 has value 3, 3 plus 1, 4, 4 is larger than 3. So no way we can update to 9. So we go to the vertex 9, nothing can be updated again. So we've done algorithm. As soon as queue is empty, we've done. So note that we visited all the vertices except vertex 5. That vertex is unvisited and actually unreachable. So this vertex is unreachable. So it means that we're not going to visit it. Um, that's where we can actually check the connectivity as well. But just DFS is quite simpler. Okay, so the way we implement that, the way we understand that it is unreachable is we see that it is infinity here. Okay, so it left unchanged. So where we can implement the BFS algorithm is following. So we have a queue of integers. We push the start vertex. It could be given from the input, or you could set it to 1, doesn't matter. Like it usually depends on the problem what is start. It may actually note that it may that the start could be anything. Like the start could not be only one vertex. We can push initially to the queue several vertices. Actually, that's the solution to one of the problems, like some of the problems that usually gives to the DFS algorithm. Okay, so we start. So as I told you before, we set initial conditions for array D and Q. So we push start vertex to the queue. That's the only vertex that would be in the queue from the beginning, and we set its distance to 0 because distance from start to start is 0, and for all the vertices that are not equal to start we set infinity. Okay, then we will proceed until the until q is not empty. Oh, vice versa. Until q is empty, we do. Um, So if vertex v, so we take the vertex from the top, you will remove it, and then for each edge, for each neighboring vertex u, like so for each outgoing edge, if it's directed graph, or just if it's undirected graph, it's just a neighbor. So for each vertex u reachable by an edge from vertex v, we check if du larger than, yeah, is dv plus 1. If so, vertex v is now proposing to all its neighbors its value, like dv plus 1. Okay, if du is larger than this value, so dv plus 1 is actually better than they got, but the only thing that they can get is infinity actually. We will see that in a moment. So dv plus 1, then du equals dv plus 1. So we set that value. We say that okay, u has this value, and now we push it to the queue. So everything as was explained in the example. Okay, this is the algorithm. And so the complexity of the algorithm is big O of n plus m. The proof is the same as in DFS. We visit each vertex only once, and each edge is looked up twice. Okay, so big O of n plus m. And one more thing that we need to do, you need to know, is why it is shortest path actually, and why, for example, why here we can replace it. We can replace this line, for example, with just we can replace with du is not is equal to infinity. So this if could be replaced with this if, and that would be the same. So let us show that the shortest path, actually this is an exercise. This is a very good exercise. Exercise, proof prove correctness of the algorithm. So um, I ask you pause the video and try to prove it. Like you should provide the argumentation why whenever I add the vertex into the queue, the value I put it into there, it is actually the shortest path algorithm. Okay, so try to prove it. Okay, so the proof goes as follows. Um, assume so the proofs follows by induction. So assume this is the start vertex. So this is the start vertex. So for the start, initially the distance is correct, right? So dv value is actually the shortest path to the vertex start. From start to start, it is 0, clear. Okay, so now the induction hypothesis is that all this region marked with this uh, blue region is so the vertices within it are correctly valued. So uh, d value for the vertex, let's say like a, so dA is correct if a lies in this region. Okay, dv is actually the shortest path to that vertex. So let us pick up the vertex u that we added to the queue. So assume we added vertex u to the queue, and its value is du. Okay, and let us assume it is not correct. It is larger than the shortest path value. So let us take the shortest path from vertex start to u and assume, so it goes like something like this. So it goes by this region and then it leaves the region and goes to u, right? So let the vertex w is going to be the first vertex that is out of that region. The first vertex on this path that is on the shortest path to the vertex u that is out of that region. All right. So the claim is that then this vertex, since this is the neighbor of that h, so this is also a neighbor of that region. So this is so this vertex is also must be added into the queue. So it must have like the value dw and uh, yeah, it must have the value dw, and but this value is not. This value must be the shortest path because um, so this value must be the shortest path. Must be because if it's not, then this entire green path was initially not the shortest path, but since it is shortest path, but if it's not the shortest path to the vertex w, then must be some other path to that vertex that goes to uh, that goes by shorter path to that vertex. But since then it means that initially this green path was not shortest. So once again, so if dw is not the shortest path that vertex, then it means that there must be some green um, there must be some green some red path that goes to w. Okay, uh, something like this might happen actually. So dw must be the shortest path, and since this is the shortest path, then this value is correct, right? And once again, the path to the w must be the shortest, since it is already lying at the shortest path to the vertex u. So if there is shorter path to vertex w, then it means that there is a shorter path to the vertex u, but we already assume that this green path is the shortest. So it means that w has the shortest path to it. So this is the shortest path to w, and that is exactly the value of dw. It must be exactly the double of dw, the value of dw. It means that this is the correct value, and this value is strictly less than So dw is strictly less than du. Then it means that dw must have been already processed. All right. So um, so dw must have been processed. Uh, but since that doesn't happen, then it means that the shortest path would be actually exactly as this. So there is no this these edges. So it means that it must be directly. So the shortest path must look like going inside of the region and then go straightforwardly to that vertex. And that is exactly what algorithm does. Okay. So you can think of the BFS actually, you can think of the BFS as sometimes it is called wave algorithm. So you can think of it as uh, mm, as the wave algorithm, right? So you first visit these vertices, you first like process this vertex, then this vertices, then this vertices. So vertex at distance 1, then vertex at distance 2, then vertex at distance 3, and so on. Okay, so if the graph is planar, this will look exactly like this. And or otherwise, you can think of you fire up this vertex, and then second by second, the fire spreads in the graph, and you just simulate it. All right. So BFS complexity is false. So by the BFS, you can solve shortest path problems. So whenever shortest path is the number of edges involved, so you can solve the shortest path problems. But with the BFS, you actually can find the shortest path. Not only the length of the shortest path, but you can actually find the shortest path just by remembering from which vertex you got the information. So whenever you set here du equals dv plus 1, you also can set here, you can set here, for example, uh, parent of u equals v. So you just remember who gave you this information, who gave you this shortest path, so which vertex propagated its result to you, so if you are the vertex. And remember, in that information, you can retrieve any shortest path from start to vertex, from start to the vertex. For example, at the vertex 8, you remember that you updated it from 4, so you just go to 4, then you go to 2, you go to 1. You can obtain the shortest path in any way from any vertex. Okay. So complexity, shortest path problems, and for example, one of the problems that were a surprise to me when I discover such problems is when I was at first course, of course, is for example, you're given the labyrinth in such way, in such so you're given the labyrinth as an input. So these are dots. Uh, and you need to find the exit, the shortest path to the exit. So you can find the path just by with BFS, assuming that the cells are the vertices and the edges are the transition between the neighboring vertices, neighboring cells. So each cell can have four transitions, so four edges to the neighboring cells. But if there is a hashtag at the cell, then you cannot have an edge from here. So you just don't add the edge. And if it's the border of the board, then you also don't add the edge. Okay, that's it with the BFS. And now we proceed. Let us implement that actually. Let us implement that. Um, sorry. Yeah. So let us rename it DFS, and then we add BFS. For the BFS, we will require what we have. So we have the same the adjacency list. So we'll need add a D, and we will need Q. Okay, we can create Q on. So we also need to start vertex. Start. Okay, just st. So let us say like this, and let us say we have start vertex. So what we do, um, oh, I'm sorry, we set start to 0, and we set all the vertices to infinitive, and then start to 0. D of I is equals to infinitive. So let us create the constant infinitive, which is going to be like very large number, 1 milliard. Okay, D of st, and while oh yeah, we create the Q. I should probably include Q. We create a Q, we push vertex st to the Q, and while Q is not empty, we do int v equals Q top, Q pop, and if yeah. So and now we iterate over the neighbors of the vertex, and if du is not equal to infinitive, so if it's not visited yet, so we use array d as was array as indicator if the vertex was visited or not. So du equals dv plus 1. Oh, sorry. If du equals infinitive, then du equals dv plus 1, and we push the vertex u to the q. And at the end, um, we just output uh, all the numbers I di. Okay, let's say oh, okay, if it equals to inf, then di, then minus 1, otherwise di. Q top, wait, Q front, sorry, this is Q front. Top is for stack. Bfs.out. Let us add the vertex that we're gonna start from is vertex 1, say. The graph is the same as for DFS. I'm sorry. Oh, this is G of BFS AI. So yeah, let us see the graph and what we have calculated. So the graph is looking like the one from DFS. So this one. So distance shortest path to 1 is 1. 4, 5, 6. 4, 5, 6 is 1. 7, 8 is 2. Because yeah, 7, 8 is 2. And 9 is 1. Minus 1. D of 9 is D of 2 and D of 3 is minus 1 because we cannot reach those vertices. Okay. That's it for the BFS. And finally, the third thing we're going to study is topological sort. So imagine the typical problem. You are given n disciplines, so topological sort. So you're given n disciplines at the university. So imagine you are arranging your disciplines on your own. And some of them have relations like discipline A is the prerequisite to discipline B. So it means that you can study B only if you have studied A. So you must study A first and then at some point discipline B. Okay, and the problem is to find any correct order of disciplines. So you need to find correct order of the disciplines. Okay, so the solution would be the first step is to find the disciplines. Associate, like identify disciplines as the vertices of the graph. So we build the graph. Disciplines are the vertices, and prerequisite relations are directed edges from A to B. So like discipline A is prerequisite to discipline B. So I draw the vertex from vertex A to vertex B. I draw the directed edge from A to B. So what you need to find then, what is the correct order of disciplines? You need to find order of vertices v1, vn such that if there is an edge vi, vj in among these vertices, then I less than j. Okay, so picturesquely, you need to find the order of the vertices such that if at position I and position j there is such edge between these vertices at these positions, then it must look to the right. So all edges must look to the right. So no edge going backwards, only forward. Okay, that's the problem. And solution is simple. So such order is actually called a topological order. Oh, I'm sorry, topological order, or otherwise, like shortly, it is called top sort. You need to find top sort of the graph. Um, First, we need to think of is that if graph is not a cyclic, then there is no such order. If there is a cycle in the graph, meaning that there are three disciplines like math, I don't know, no, without examples, A, B, C, and you need to study A before B, B before C, and C before A, then it means that you cannot, like, there's no such order that would satisfy all three requirements. Okay, so if the graph is acyclic, if it's not acyclic means no cycle. If a graph is not acyclic, then it means that no such order. If there is a cycle, in other words, if there is a cycle, then it is no such order. Okay, in case if it is acyclic, then for example, uh, let us let us consider this example. This is an acyclic graph. So acyclic graph can be drawn from top to bottom like this. All the edges are going downwards because there's no cycle. There would not be the edge from bottom, like from bottom to top. So I know that there are a lot of topological sorts. There are a lot of top sorts. For example, 648135572, 648135572. This is the topological sort because all the edges are going forward, right? For example, H17, 1 to 7, H3, 2, 3, 2, right? You can pick up any edge from this graph and you will see that those two orders will have these edges from left to right. And for example, if you take the first topological order and then you swap 1 and 8, we put 1 here between 4 and 8, then we'll have this topological order again. So this is again topological order. It does not omit any conditions. So there are a lot of topological orders. Um, this is actually an open problem still. For a given graph, count the number of topological orderings in an effective way. Um, but yeah, this is very interesting object of study in mathematics. Okay, but we will do the basic things. So how to find the topological order, some certain topological order, like any topological order. So what we're gonna do, we're gonna run the DFS for each vertex, for each unvisited vertex, like we did for the search of connected components. And we pass to this DFS like some vector, and we'll add vertices to that vector before finishing the DFS. So at the end of the DFS, we'll add this vertex. This is called, we'll store them by I out time. So each vertex, for each vertex, we can define in time and out time. That is the time we run the DFS in that vertex and the time we left the DFS from that vertex. Okay, but okay, do not bother you with this time thing. Um, um, like just code-wise, that would look like this. So we pass TS stop sort some vector to the DFS. So we pass it with an ampersand, as you may understand. So we pass it with an ampersand. So it means that it is modifiable. So if it modified here, it modified wherever it was passed as an argument. So yeah, so this is the basic DFS. Just we add TS pushback at the end. So we add vertices at the end of the DFS. Whenever we leave, right before we leave the DFS, we add the vertex V to this. So and from the main, we will run this. from the main function, we'll write this. So we create the vector. If it was, if from for I from 1 to n, if it's not what, if it wasn't visited, then we run DFS from that vertex. And at the end, we reverse this top sort. I will explain why. So let us run this algorithm for this graph. This is exactly the same as before. So we start from 1, we go, so we start from 1. I just running this code. I equals 1, if it's not visited, dfs I ts. So I start from 1, I go to 5, I'll go to 7, right? That's it. From 5 and 7, I cannot go anywhere, so I finished with 7, I finished with 5, I finished with 1. Also, yeah, when sorry, once again, I start from 1, I go to 5, I add 5, since I finished in 5. Then I add 7, I finish at 7. Then I add 1, I finish at 1. Then I go to vertex 2. The next one is going to be the vertex 2. Vertex 2, it is done. No edges outgoing, so 2. Um, then vertex 3, it is done as well. 3, um, because 7 and 2 are already visited, have been visited. So vertex 4, um, I add the vertex 4, all neighbors are already visited. Vertex 6, vertex 8, in same fashion. So as you can see, let us draw the graph. Let us draw all the edges: 1, 5, 1, 7, 1, 5, 1, 7, 2, 2, no, 3, 3, 2, 3, 7. What else? 4, 4, 1, 4, 3. Okay, let's say 4, 1, 4, 3. Um, 5, 7, 5, 6, 6, 1, 6, 1. 7, nothing. 8, 3, 8, 2. Let's say 8, 3, and 8, 2. Okay, so as you can see, all the edges are going are watching to the left, so they're turned to the left, and so that's why we reverse it here. After the reversal, we'll have all the edges looking to the right, and that's it. That's the way we obtain the topological sort. And now let us understand why the, okay, first of all, what is the complexity? Pause the video and answer this question. 1, 2, 3. So the complexity, of course, would be big O of n plus m, because n is, I mean, we visited each vertex once, and we visited each edge, like we traversed, we iterated over each edge once, only once in this case, because the graph is directed. Okay, and now, um, hmm, interesting, yeah. So yeah, now, so now let us understand why all the edges are looking backwards. Actually, this is the next good exercise. I will explain it in a moment, but think of it as it on your own, why it works. Why it works. Why it works. So, um, so the reason why it works is the following. Um, so let us see what happens whenever we add the vertices in the DFS. So, um, yeah, even more. So for each edge, so what we need to what we need to show is that for each edge, for example, like this one, 3, 7, yeah, there is a such edge. Yeah, so for this edge, we need to ensure that after all the DFSs, this edge would be looking to the left, right? All we need to determine is that. And that follows by the fact that, by the order in which like just from the DFS, right? So if there is an edge and um, if there is an edge like this, so this is V, this is U, two ways can happen. First one, U is already visited, U is visited, then it means that um, U is visited, then it means that it is already in TS. So that means that whenever we finish with V, U is already there. So V would be to the right of the U in TS, right? So yeah, first of all, assume that we entered the vertex V and there is an edge outgoing from vertex V to vertex U, and we need to verify that U is going to be to the left of V. So first first case that U is already visited, then it means that it's already in the TS, but I haven't yet added V to the TS because V is not over yet. Then it means that U is already there, V is not yet there. That means that V would be to the right of U, right? So this H would be going to the left. The second case is U has not been visited, then it means that I go to U is not visited. Then it means that I go to U and then I leave U. Maybe I traverse something, then I leave U and I go to, and I then, so I finish U first and then I finish V. So that's the property of the DFS. I first finish U and then finish V. So finish U, then finish B, finish V. Hence, in the top sort, the H would look like this. So since I picked up the arbitrary H, it means that is going to be satisfied for any H in this TS list. So it means that that is going to be the reverse top sort, right? So if I reverse this graph, reverse this vector, that is going to be a top sort. So I'm not going to implement that since implementation almost the same as the usual ordinary DFS. And that's it for today. Thank you for your attention.